We now study about duals of Hilbert spaces. So we have the following theorem. Again, it's called the Rees representation theorem. Because it gives you a representation of the dual element of the dual. Okay, so let H be a Hilbert space. Let phi belong to H star. Then there exists a unique y in H such that phi x equals xy for all x in H. Further, norm phi equal to norm y. Okay, so this is the, so we already saw that if you have y in H, then f sub y given by x comma y, inner product y, gives you a linear functional whose norm is equal to the norm of the vector. Now we say that every linear functional occurs in fact in this fashion. So that is the so proof. So if y is in H, then fy of x equals xy defines a continuous linear functional, and norm of fx by the Cauchy-Schwarz inequality, norm of fy, sorry, equals norm of y. This we have already seen in an example last time. Okay, so now we have to show that every mapping occurs in this way. So if you take the mapping phi from H into H star, okay, namely y, phi of y equals fy. So this is an isometry into H star. So the image of phi is closed, and all we have to show phi is onto, so enough to show image of phi is dense. Since it's already, image is already closed, since you have an isometry, so it's enough to show that the image is dense. Okay, so that will complete the proof. So you consider a linear functional let us say psi on in belonging to H double star, which vanishes on image of phi, to show psi is equal to 0. Okay, but H Hilbert spaces are uniformly convex, and therefore implies they are reflexive. H is reflexive. Therefore there exists an x in H such that psi of any linear functional f is equal to f of x for every f in H star. Okay, so if you take any fy belonging to image of phi, so psi of fy is equal to fy of x, which is xy. Okay, so therefore So this implies that x is such that xy equal to 0 for every y in H. So in particular, this implies that xx equal to 0, that is norm x square equal to 0, that is x equal to 0. And that implies that psi is equal to 0, and therefore the image is dense, and consequently we have shown that phi is onto, and therefore the representation theorem is completely proved. Okay, so now we can directly prove. So proof ab initio, that means from first principles, that H is reflexive and Rees representation theorem holds. In fact, we will first prove the Rees representation theorem, and then from that we will deduce that H is reflexive. So up to now, what have we done? We have shown that we used uniform convexity and the fact that uniform convex spaces are reflexive, and from that we proved the Rees representation theorem. Here we will now directly prove the Rees representation theorem without using any machinery, and then deduce in fact that H is reflexive. It's good to know both the proofs. So let us assume that phi is not 0, not identical 0. If it's 0, then the 0 vector is there, so we don't need to do anything. So phi is not 0, so there exists a u in H such that phi of u is not 0. So now let us take v in H and then look at v minus phi v by phi u. You can divide because phi u is not 0 times u. Now this belongs to kernel of phi, because if I take phi of this, I get phi v minus phi u, phi v by phi u, and phi u will get cancelled. So phi v minus phi v will be 0, and so this belongs to kernel of phi. So this means kernel of phi equal to m has codimension 1. Namely, it is the complement of that is one dimensional. It is spanned by a vector such that phi of u is not equal to 0. Therefore, let us take u in M perp, the orthogonal complement, as such that norm u equal to 1. Okay, and now you put x equals phi u bar times u. I am doing the complex case always. So up to now in Banach space theory, I have said worked with reals, and then said the complex case is will be the same proof, and also in case there was a difference like the Hahn-Banach theorem, I made special mention of that fact. In case of Hilbert spaces, I will naturally work with complex numbers because there's this conjugation which always comes into play, and it is better to check everything with if that is okay. And then if the real case will be obvious because you don't have to put the conjugate at all. Okay, so we will always work with the complex numbers as the base field. Okay, so if you have this, let us take so any y. So let me I hope, let me not mix up the notation. So there exists a unique y in H. Okay, so let me put y. So I want to call this as y. Okay, so now let me write this. So now if you take any x belonging to H, then x can be written as m plus which is in the kernel plus something some alpha u. Okay, alpha u plus m. Okay, x equals m plus alpha u. So now let us take x comma y. This is equal to m plus alpha u times y, which is phi u bar u. Now m and u are orthogonal because m is in the u is in m perp, m is in m, so m is in m. Okay, so Therefore that is 0. So you get equal to alpha times phi u bar will come out as phi u times uu, which is equal to alpha times phi u, which is phi of alpha u, which is also phi of alpha u plus m, because m is in the kernel, I can add it, and that is precisely phi of x. So there exists always is. Okay, the uniqueness I did not prove, I should have done it even there. So uniqueness we always have, namely suppose you have two elements, you have x y1 equals x y2 equals phi of x for all x in H. Then you have x y1 minus y2 equal to 0 for all x. So you put x equals y1 minus y2, so you get norm of y1 minus y2 whole square equal to 0. This implies y1 equals y2. So you always have a unique vector. So this proves the Rees representation theorem, namely every continuous linear functional, in fact, so we have even identified what is that vector. So you have to take a vector, unit vector in the one-dimensional complement, orthogonal complement of the kernel, and then you just put phi u times u. So you may have some doubt that since it's one-dimensional, there will be two vectors, u and minus u, both with norm 1. But then if I take phi u times u or phi of minus u times minus u, it's the same. This is equal to phi u times u. So this vector will not change. So the uniqueness is not contradicted. Okay. So now let us prove the reflexivity of this thing. So now before that, let me look at the map x going to fx. Okay. So then if I take f of alpha x plus beta y times z, so that is z inner product alpha x plus beta y, which is alpha bar zx plus beta bar zy. So that's equal to alpha bar fx plus beta bar fy acting on z. So f of alpha x plus beta y is alpha bar fx plus beta bar fy. So this is a conjugate linear map, it is not just a linear map. Okay, so now we are going to define, so we have h, then we have h star. Now h star we are going to give a natural inner product on this. So define an inner product on h star. So any element of h star is of the form fx. So we have fx and fy. I am going to define as yx. Okay, so we want to check that this takes all the properties of the inner product. So let us take fy fx. This is equal to xy, which is yx conjugate, and yx is nothing but fx fy conjugate, and therefore that property is true. Now what about linearity in the first variable? Okay, so what about fx this is equal to xx, which is norm x square, which is norm fx square. We know, because we know that the Rees map, so this is called, x going to fx is called the Rees map, and that is an isometry, and therefore you have this. So we have now check about the linearity, okay, in the first variable. So it will be conjugate linear in the second variable automatically because of the conjugacy condition here, and therefore we have to take alpha fx plus beta fy fz. But this we just saw from this is nothing but f of alpha bar x plus beta bar y fz, which is equal to z alpha bar x plus beta bar y, which is equal to alpha zx plus beta zy, which is equal to alpha fx plus beta Fy acting on Z. And therefore alpha Fx plus beta Fy, so is nothing but alpha times Fx Z, Fz, sorry. Sorry, wait a minute. So this is nothing but, this is Fz, and then here you have alpha Fx plus beta Fy. Fz plus beta Fy Fz. And therefore the distributive law, linearity in the first variable, is well defined. So therefore this defines a genuine inner product on the space. Okay, so now again we can define, so H star is therefore a Hilbert space, and therefore you can define an inner product on H double star in the same way using the Rees map. Okay, so now we have two maps. Now Rees map is always on 2. So now we have two maps going from H to H double star. One is the canonical map X going to J of X. What is Jx? Jx acting on any F is nothing but F of X. This is the evaluation map. So this is one map. The other map from H to H double star is X going to F of Fx. Okay, F of Fx is a Rees map between from H star to H double star. Fx every so we have two such maps. Okay, we want to show that these are one and the same. Okay. So let F belong to H star. Then F equals Fy for some Y in H. Okay. So F of Fx acting on F is F of Fx acting on Fy, which is nothing but Fy Fx in the dual space. So this is the inner product in the dual space. I didn't put, okay, let me put a star here. Okay, and that is equal to xy. Now what about Jx of F? This is Jx of Fy, which is Fy of X, and by definition that is xy. So these two are the same. So Jx is nothing but F of Fx, but we know that the Rees map is on 2, so this means that J is on 2, and therefore H is reflexive. So we have shown that starting from first principles, we have shown that a Hilbert space is reflexive and that the Rees representation theorem is true. Okay, so now so if you look at the map, Rees map, F X going to F of X, this is a isometry, and linear if you are working with R, and conjugate linear if C is the base field. Okay, so it's not a big deal if you have a conjugate linear map, but so in particular, if H is a real Hilbert space, we can identify H with H star. Because you have an isometric isomorphism. We have been doing this repeatedly. In fact, we have already done it in case of L2, Ln2, etc. and the space L2. Okay, all these spaces we have actually identified the dual. We have often used it like that. Okay, so now the question is, can we always do it, or should we exercise some caution? So there are some situations when you should not blindly do it. Okay, so a typical situation is the following. So caution: cannot identify all Hilbert spaces with dual simultaneously when dealing with families of Hilbert spaces. Okay, so let me give you a typical example. So let V and H Hilbert spaces. Okay, and so we have norm V and norm H as the norms, and then you have the inner product V and the inner product H. Okay, such that V is included in H. That means V is a subspace of H as algebraic set, and the inclusion is continuous. That is, V is contained in H, and there exists a constant C positive such that norm V H is less than or equal to C times norm V in V for every V in H. V in V. 1 and 2, V in H is dense. So it's a dense and continuous inclusion. Okay. So now let us identify. So V and H real Hilbert spaces, let us say. H with H star via the Rees map. So we can do that, there's no harm. So the question is, can I also identify V? So can we also identify V with V star? So the answer is no, because of the following reason. Okay, so now let us take any F in H. Then consider V going to VFH. So what is mod VFH? This by the Cauchy-Schwarz, it's norm V in H, norm F in H, that is less than to C times norm F in H, norm V in V. So this is a continuous linear functional in V. So that means F belongs to F. So V going to VF generates a continuous linear functional, an element of V star. So let us call it T of F. So T of F equals TF acting on V is equal to VF acting on H. Then F going to T of F is 1 1. Why is it true? Because if you have VF1 equal, if TF1 equal to TF2, this means V of F1 minus F2 equal to 0 for all V in V, Okay, but V is dense in H implies V of F1 minus F2 equal to 0. This is H for all V in H, and if you put V equal to F1 minus F2, you will get F1 equals F2. Okay, so this is a one-to-one map. So we can consider V can be H can be thought of as the same, and norm of TF, from here we say, is less than or equal to C times norm F in H. We have seen that, and therefore this is in fact a continuous inclusion in this. Okay, now we claim that this is also dense, so we want to show that if you have a continuously linear functional phi in V double star which vanishes on H, then we show phi equal to 0. So that will mean H is also dense. Okay, why is that so? Because, well, V is a Hilbert space, so it is also reflexive. So that implies there exists an X such that phi of any F, phi of any F in V star is equal to F of X. So that means for all F in H, we have TF acting on X. Phi of TF is TF acting on X equal to 0. Okay, and what is TF? TF is nothing but, that is X F H equal to 0 for all F in H. But then V is contained in H, and therefore I can put F equal to X itself. So I get XX equal to norm X square equal to 0. That implies that X equal to 0. That means phi equal to 0. So what do we have? Conclusion. So if V is continuously embedded in H, and this is a dense inclusion, and if I identify H with H star, then I can embed, this is also embedded, and this inclusion is also dense. Now if I also identify these two, then that will be absurd, because if V equals V star and you have H in between, then all of them are equal, and that you know they are not. Okay, so it is not correct to identify. So when you have therefore a family of Hilbert spaces which are connected to each other like this, then we choose one space which we call the pivot space, where we identify the space with the dual, but all other spaces you will have that the duals are same. So this, when you study, especially in the case of Sobolev spaces, this will be the case. Okay, so we will have a Sobolev space called H10. There will be spaces like this, H20 contained in H10, which is contained in L2, and that we will assume is its dual, and that will be H-1, that is the dual of the space, contained in H-2, which will be the dual of the space, and so on. And therefore we will have a tower, a whole chain of Sobolev spaces and their duals. We will not confuse H1. There is a Rees map when you want to only study these two, but when you are studying it together with L2, you must have only one function, one space which is identified, and the other spaces should not. Okay, so we will continue with this.